You can see the screen.
Yes, sir.
In the last classes, actually, I have covered substantial portion of the estimation theory. So we started with all the basic concepts, and then we have gone up to the UMB-UE, and then also I introduced the concept of invariance, and we found the best invariant estimators, either location or scale or linear invariance. Then I also introduced some additional concept like base estimator and minimax estimator. However, actually the time is very short in this semester somehow, because I think the exams are starting from 6th April itself. Earlier it used to be from 20th April, but somehow it has been preponed by 2 weeks. So I will have very little time. So let me start a testing of hypothesis. Otherwise, I won't be able to cover even a small portion of it. So what is a statistical hypothesis? So a statistical hypothesis is actually an assertion about the distribution of about a probability distribution. So a statistical hypothesis is an assertion about underlying probability distributions. Let me start with something very simple. So for example, you have a coin and you want to know whether the coin is fair or not. Okay. So what you will do? So fair coin means the probability of success is half, and if it is not fair, then it is not equal to half. So it could be less than half, or it could be more than half, where P is the probability of observing, say, head. Now, in order to do this thing statistically, how would you proceed? You can conduct random experiment of actually tossing a coin some number of times, suppose 5 times or 10 times, and you observe how many times the head has occurred and how many times the tail has occurred. If the number of heads and tails are quite close to each other, then you would feel that P is equal to half is a fair assumption. And if it is not, then you will feel that the coin is biased, either in favor of head or in the favor of tail. So a very simple looking statement can be converted to a direct probability problem in the following way. So suppose I say X is the number of heads in tossing of a coin, and we conduct the experiment certain number of times. So suppose I say I conduct say the experiment say 10 times, and we P is the probability of head, okay, in a single trial. Then what is the possible hypothesis testing problem? How I will write it? So some symbol I am writing H naught P is equal to 0.5 against say H1 P is equal to not equal to 0.5. So this is called null hypothesis. This is called alternative hypothesis. So the question is that, of course, you can ask that why should I consider two hypotheses? Okay. So statistically speaking, what happens that when you say that I want to test something, so like you want to say whether the coin is fair or not. Okay. So then you say that I want to test P is equal to half. Now, if your experiment suggests, I had given example in your probability course also, that certain experiments of this nature were conducted large number of times in 1920s and 30s, etc. Or even if you look at current status, there are experiments like checking the average birth rate of males and female childs. So there also, because the experimental values are available over a long period of time. So what were you testing? You are testing p is equal to 0.5. But then the question is that why should I write another one h1 that is p is equal to not equal to 0.5? The answer is that if my data suggests that p is not equal to 0.5, then I should specify that. That means if my hypothesis to be tested is not supported by the data, then something else is supported, and that should be mentioned. So that is the concept of considering two hypotheses. That is, one is called null hypothesis and other is called a alternative hypothesis. Now, a reasonable procedure for this, maybe you can propose it like this. We can say that we will accept h naught if, say, 4 is less than or equal to x is less than or equal to 6. That means if the number of heads is between 4 to 6, then we feel that the coin may be fair, and we will accept h1, or you can say reject h naught if x is either less than 4 or x is greater than 6. Okay, so this is called rejection region or critical region, and this is called acceptance region. So what is a test of hypothesis? A test of hypothesis is a rule based on certain test statistics. So x here is test statistic. Which partitions the sample space in two parts. One is called acceptance region and another one is called rejection or critical region. So various kinds of testing problems are like that. There is some severity of the COVID disease. For example, in Indian condition, you can say that there were 3 phases. Okay, first phase, second phase, and the third phase. Okay, so one would like to test whether the severity in the second phase in the terms of mortality was more than the first phase or the third phase. Similarly, you may like to test that if say I say mu is the rate of infection. So the rate of infection in the third phase is higher than the rate of infection in the second phase, and that is higher than the first phase. Okay, so one may like to test this hypothesis based on the data. I mean, I can make some statement, but then I need to test it based on the data. Okay. For the 3 phases. Okay, so I may like to write like this. Suppose mu I is the rate of mortality of COVID infected persons during phase I, where I is equal to 1, 2, 3. So one hypothesis testing problem can be whether mu1, mu2 and mu3 are same, or mu1, or you can say, let me put it in the reverse way. Mu3 is less than mu1 is less than mu2. In the first phase, mortality was more than the third phase, and the second phase was mortality was. So this could be one hypothesis testing problem. Okay. Similarly, if I consider, say, theta I as the rate of infection. Rate of infection is that if a person is infected, then how many people he can infect. So in statistical terminology, it is called some R naught value. So let me say, if theta is the rate of infection during phase I, for I is equal to 1, 2, 3, then a hypothesis testing problem could be written like this, that whether they are same in all the three phases, or again the rate of infection in the first phase was less than in the second phase, and it was less than the third phase. So this could be one hypothesis testing problem. Okay. Do you have any questions till now?
Sir, is there any basis to choose the null hypothesis?
Okay, yeah, that's a good question. So null hypothesis simply means that some original statement that we want to make. As I already mentioned, that just writing one hypothesis is not enough. We should actually specify two hypotheses, in the sense that if my original assertion is not okay, then what else is okay? See, for example, here if I have written theta 1 is equal to theta 2 is equal to theta 3, alternative could also be that theta 1 is not equal to theta 2, or theta 1 is not equal to theta 3, or some of them are not equal, or all of them are not equal, etc. But here I feel that genuinely that theta 1 could be less than theta 2, less than theta 3 based on our experience. So now I want to test it based on the actual data that is available. Okay. So now you may say that why not I put H1 in place of H0 and put H0 in the place of H1. So the answer is yes, it can be done. There is no hard and fast rule that what is H0 and what is H1. Okay. It is only some basic assumption that we generally put as H0, and some alternative assumption then we put it as the H1. But when we actually write the test of hypothesis, then procedures for certain type of tests can be developed easily. For certain type of test, it is difficult to obtain. Okay. So like the problem which I have just now written here, actually these are active research problems. In fact, these are all active research problems. And in fact, now also I have some student who is actually working on these problems. Of course, they are working on some general models where these are part of that. Okay. Is your question answered?
Yes, sir.
So let me go back to the example and yeah. Let me go back to this problem which I gave. So this is binomial distribution. Like in order to test whether p is equal to 0.5 or p is not equal to 0.5, I set up a test here. I set up a test in this way that if x is, that is the number of heads out of 10, is 4, 5 or 6, then I will accept H0. Otherwise, I will reject H0. Okay. Now, when we are taking the decision about a population parameter based on a sample, there is a chance that I might have made a mistake. That means maybe x is equal to 6 and I accept H0, but actually it may be that P is not 0.5, P may be 0.6 or maybe 0.7. Okay. In that case, H1 is true, but actually I am, based on my test function, I am actually accepting H0. On the other hand, it is possible that suppose I get x is equal to 3. Suppose there are, I mean, it's a coin, fair coin, and 10 times I tossed, I got 3 times head. So I feel that, okay, based on my procedure, I will say that it is not a fair coin. But actually, it may be a fair coin, and if I had conducted trial, maybe in place of 10, I would have conducted 50 times. Then I would have got nearly 25 times head, or maybe 24 times head, etc. It is possible. That you might have noted sometimes, and as a curiosity, you are all young people, you might be observing this role of toss during a cricket match. Okay, so whenever a cricket match is there, there is a toss, and the captain who wins the toss, he decides whether he will bat first or he will field first. Okay, and sometimes this result is actually told in a prominent way. For example, last year when I think some championship was there, probably it was either maybe 2020 championship or maybe 50-50 championship, etc. It was observed that the Indian captain kept on losing the toss in continuation. So does it mean that the toss was based on the unfair coin? Okay, so this could be a conjecture, and one can try to test that kind of thing. So that means in using a test based on sample to accept or reject a hypothesis, we can make two types of errors. So I am just using the name type 1 and type 2, which is the popular name for such errors. Okay, that is rejecting H0 when it is true, and alpha is the probability of type 1 error. That is the notation. And type 2 error is accepting H0 when it is false. And the usual notation for probability of type 2 error is beta. I will introduce another concept, that is gamma, that is 1 minus beta. That is probability of rejecting H0 when it is false. This is called power of the test. Let me explain these things. So you would like to have a test procedure for which alpha and beta both are 0, isn't it? Why should you have error in your procedure? However, in reality, it is not possible, because your type 1 error occurs due to sampling, because you have taken a sample and that may lead to an error. Similarly, type 2 error is also based on the sample. So it is impossible to have alpha and beta both to be 0. So now what is the next best thing? The next best thing is that you consider several test procedures for which both alpha and beta are the smallest. But due to the nature of definition of alpha and beta, it is not possible to minimize both of them simultaneously. The reason is that alpha, that is the type 1 error, occurs when you are rejecting H0 when it is true, whereas type 2 error occurs when you accept H0 when it is false. So the regions rejecting and accepting, they are complementary. So if you try to reduce type 1 error, that means you will try to reduce alpha. If you try to do that, then naturally the region for accepting H0 increases. Although it is under falsity of the hypothesis, but the region has increased. Therefore, in general, if alpha is reduced, beta will increase and vice versa. So in a real problem, it is impossible to control both types of errors. So a practical solution was proposed, that you propose such a thing that one of the errors can be kept fixed. For example, you say that I would not like to make, say, type 1 error more than 1 in 100 times or 5 in 100 times. Okay. Now, if we fix a upper bound for alpha, then find out other test procedures for which alpha is bounded by 0.05, but beta is minimized. If you say beta is minimized, then 1 minus gamma is maximized, 1 minus beta, that is gamma, which is the power of the test. So it gives you the concept of most powerful test procedure. Okay. In practice, it is not possible so we fix alpha to be, say, alpha naught and find that test procedure which minimizes beta, or you can say maximizes gamma. This is called most powerful test, that is MP test of size alpha. So this alpha that we are fixing, this is called the size of the test. It has some other names also, level of significance or significance level, etc. Okay. This concept of type 1 error, type 2 error, the power of the test, these are all developed by the actually two statisticians by name Jerzy Neyman, who lived from 1894 to 1981, and Egon S. Pearson, who lived from 1895 to 1980. Okay, so in a collaboration, they developed all these things, and the first result is actually named after them as Neyman-Pearson fundamental lemma. So they had actually collaboration in 1926 to 1936. During these 10 years, the entire modern theory of testing of hypothesis was developed by these two statisticians. So let me give this fundamental lemma now. The statement of the fundamental lemma is as follows. Let pi naught and pi 1 be two populations with either PDF or PMF. Okay. and we name them as say f0 and f1 respectively. Then for testing hypothesis, that is fx is equal to f1x, f0x against alternative, that is fx is, that means whether the density is f0 or f1. Okay. The test, the most powerful test, let me call it phi, is given by phi x is equal to 1 if f1x is greater than some k times f0x, and it is equal to 0 if f1x is less than or equal to k f0x. Let me not put less than or equal to. So what I will do, in between something is left out. Okay. So I will show you what it is. Is given by this, where k is chosen such that probability of type 1 error is equal to alpha. Okay, so now let me explain this. What is this phi function? So phi function, actually it is equal to 1 if h0 is rejected, and it is equal to 0 if h0 is accepted. Okay. Now this is very important statement. The test functions notation we give like this. So basically we are saying that if I want to test the hypothesis f0 against f1, then you will reject h0 if f1 is greater than some k times f0x, and we will accept h0 if f1 is less than k f0x. Now you may ask that I have not written what happens when f1 is equal to k f0x. So in the case of continuous distribution, actually this will not make any difference whether you put equality here or you put it here. In the case of discrete distribution, because sometimes the probability of a point may not be achieved, therefore that in between we will put some numerical value here. I will show you it through some example. So this is the most powerful test. Now this lemma actually laid the way that how to construct the most powerful test in any given testing problems. So I'll explain through some examples how it is done, and then how they have led to the modern test which you read in all the books, and they are actually incorporated into all the software packages. Okay. So let me start with some simple example. Okay, so let us consider, say, note here that this is the most powerful test. So this form itself is important here. So let us consider one exercise. Suppose I have a random sample from a normal distribution, say from mean mu and variance I am taking to be known. So I have put it 1. Okay, and we want to test say h0 whether mu is equal to some given value mu naught, and against whether mu is another value mu1. Okay, here of course you may have mu1 greater than mu naught or mu1 less than mu naught and so on. So let me just put it here one case that mu1 is greater than mu naught. Then according to this Neyman-Pearson fundamental lemma, I should write down the f function at these 2 points, which I will call f0 and f1. So now you go back to your likelihood function, the sufficient statistics, the measure of information, and so on. Everywhere, what was the basic expression that you wrote? It was the joint distribution of x1, x2, xn. Okay. So the joint PDF of x1, x2, xn is, okay, so I'll write it at joint value. So that is x is equal to this. You remember it very well. 1 by root 2 to the power n minus 1 by 2 sigma xi minus mu square. You remember, all of you, this thing, because we have written so many times this. We wrote it for MLE, we wrote it for Rao-Kramer lower bound, we wrote it for the sufficiency, we wrote it for minimal sufficiency, we wrote it for completeness. For everywhere we have written it. Is it okay? This joint distribution of x1, x2, xn?
Yes, sir.
Now you have to say f is equal to f naught or f is equal to f1. So what is that? F naught means it is corresponding to mu is equal to mu naught, and f1 means it is corresponding to mu is equal to mu1. So we will write this ratio here, that is f1x by f naught x, because what is the region of rejection? That f1x is greater than k times f naught, and acceptance region is f1 is less than k times f naught. So we just consider the ratio. The ratio should be greater than k or less than k. All right. So if you write down the ratio, this 1 by root 2 pi to the power n will naturally cancel out, and here it is e to the power minus 1 by 2 sigma xi minus mu1 square divided by e to the power minus 1 by 2 sigma xi minus mu naught square. Okay. And again we can do some simplification. So what is the rejection region? Let me call it some name I will give here. I write it as lambda. Okay. So we reject h naught, that is phi x is equal to 1 if lambda x is greater than k. All right. So this lambda, it has actually this e to the power, where k is a constant, where probability of lambda x greater than k under h naught, that should be equal to alpha. This is the condition that we are having. So what we can do, this is greater than k, k is a constant, I can take log on both the sides to simplify the terms. So it will reduce to half times sigma xi minus mu naught square minus sigma xi minus mu1 square greater than log of k. So this sigma xi square minus n mu naught square plus, sorry, this is plus here, minus 2n mu naught x bar, and then second part if I write, that is again sigma xi square plus n mu1 square minus 2n mu1 x bar, and this 2 also I take to the right side, so that is 2 log k. Then this term cancels out, this n mu naught square, n mu1 square, these are all constants. So this is reducing to something like x bar into mu1 minus mu naught is greater than some c. See, some coefficient is coming, that coefficient I have changed it, because this term I am adjusting, then 2n is there, all those things I am changing here. And since I am taking mu1 to be greater than mu naught, then this part also I can remove. So this is reducing to say x bar greater than say some c star, where probability of x bar greater than c star is equal to alpha under h naught. Now under h naught, that is under when mu is equal to mu naught, under h naught what happens? You are having x bar following normal mu naught 1 by n. The distribution of x bar is normal mu 1 by n, that is sigma square by n. sigma square is 1 here, and when mu is equal to mu naught, that is when under H naught, this is the distribution that you are having. So this probability statement we can write. So this statement 1 is equivalent to probability of root n x bar minus mu naught greater than root n c star minus mu naught, that is equal to alpha. So since root n x bar minus mu naught has a normal root n x bar minus mu naught is actually z, that is following normal 0, 1. So this point actually you can consider this as z alpha. So this probability is alpha, isn't it? This is the CDF of the standard normal distribution. Okay. So what is this point? That is nothing but z alpha. So the test procedure is reject H naught if root n x bar minus mu naught is greater than z alpha and accept otherwise. Is this derivation clear to you? Do you follow this derivation?
Yes.
Now you see, let us look at the interpretation, how I got this thing and why this is a natural thing. So what is happening? You are rejecting actually, what is the rejection region? Rejection region is if x bar is greater than something, okay, and accepting otherwise. So you look at this hypothesis framing here. The framing is that mu naught is less than mu 1. That means the null hypothesis supports a smaller value of mu, and alternative hypothesis supports a bigger value of mu. Okay. Now again you go back to your concept of sufficiency, MLE, and so on. So for the mean of the normal distribution, what was the better estimator? It was x bar. X bar was MLE, it was UME. We also proved it is best translation invariant estimator and so on. It is based on the sufficient statistics. X bar is complete and sufficient actually. So naturally, in order to take a decision on mu, I should make use of x bar. Since the null hypothesis supports a smaller value of mu as compared to the alternative hypothesis, therefore the smaller values of x bar should support the, that means when the x bar value is comparatively less or comparatively small, then I should go for H naught. And if x bar is somewhat larger, then we will go for H1. The question is that somewhat less, somewhat more, these are all verbal things, like what is smaller for me may not be smaller for you, or what is larger for me may not be larger for you. So in order to have a statistically crisp statement about this one, we made use of this most powerful test theory, where probability of the type 1 error is fixed to be alpha. So if we fix that probability to be alpha, then this point can be precisely determined. That means here you are getting x bar greater than z alpha by root n plus mu naught. So that is the cutoff point. See, x bar greater than z alpha by root n plus mu naught. This is the rejection region. See, I have to test whether x bar, that is the mean, is mu is equal to mu naught or mu is equal to mu 1. But how much big mu 1 is compared to mu naught, that is not known. So that part is answered by this thing. So to taking this argument further, see if it was other way around. For example, if mu 1 was less than mu naught, then the result will be on the reverse direction. So let us see that thing. Suppose here mu 1 is less than mu naught. Then from here, x bar into mu 1 minus mu naught greater than c, it will become x bar less than C star, because if mu1 minus mu naught is negative, then if you take it to the other side, it will become the reverse region. So in that case, then the rejection region for most powerful test is x bar less than some C1, I can say, okay, where probability of x bar less than C1 under H naught is equal to alpha. So if you utilize this, then this is probability of root n x bar minus mu naught less than root n x bar minus C1, that is equal to alpha. That means it is on the left side now. If this is your standard normal PDF, then I am saying, so this point that is on this side, so minus Z alpha. So this probability will be alpha. So this means root n x bar, sorry, I made a mistake here. Yeah. This is C1 minus mu naught. Yeah. So root n C1 minus mu naught is equal to minus Z alpha. So the rejection region is root n x bar minus mu naught less than minus Z alpha. Or we can put it in this way also, x bar is less than mu naught minus Z alpha by root n. So you see here that it is not something like symmetric, that if mu1 was less than mu naught, then I would have just reversed it. That I could have done it for x bar less than mu naught plus Z alpha by root n. No, it has become mu naught minus Z alpha by root n. So essentially it means that around mu naught, actually I am placing a region actually, that is Z alpha mu naught minus Z alpha by root n to mu naught plus Z alpha by root n. Within that portion, actually I am going for mu naught. Outside that, I am actually going for alternative. Okay. So later on, when we will consider generalized testing of problems, there you will see that these type of tests are derived using Neyman-Pearson theory. Okay. So if this is okay, I can proceed further to some other example. Is this example clear to you?
Yes.
So in a given problem, what happens that you are given a sample, you will calculate this test function and compare with the cutoff point. Cutoff points are available from the tables of the distributions. Okay. Let me take another exercise. The other problem that we have repeatedly solved is about the variance of a normal distribution. Okay. So let us go for that. So I am considering the simplest case where I take one parameter case. So the mean I am taking to be 0, so that it becomes simple problem. And I want to test about sigma square. So that means sigma square is either some value sigma naught square, or sigma square is some different value. Let me call it sigma 1 square. Okay. And again, you will have two cases, that is sigma 1 square can be greater than sigma naught square, or sigma 1 square can be less than sigma naught square. Okay, two possibilities are there. By Neyman-Pearson lemma, the test function will be based on the ratio of the probability density functions of x1, x2, xn at two different parameter points, that is sigma 1 square and sigma naught square. So the joint PDF, again this has been written repeatedly in your various concepts that I have done so far, that is the likelihood estimation, then we have done this lower bounds, then we have done this sufficiency, then we have done minimal sufficiency, and then we have done completeness. In each of those concepts, we have written this joint distribution of x1, x2, xn here. So that is fx equal to 1 by root 2 pi sigma to the power n e to the power minus 1 by 2 sigma square sigma xi square. Since mu is 0, so that term will not come here. So f1 by f naught, okay. So this 1 by root 2 pi will get cancelled out. 1 by sigma 1 to the power n e to the power minus 1 by 2 sigma 1 square sigma xi square divided by 1 by sigma naught to the power n e to the power minus 2 sigma naught square sigma xi square. Okay. So rejection region is for the most powerful test that lambda x greater than some k. Now in the k, this sigma naught, sigma 1 and all that we can adjust, we can take log also. So if we do that, it becomes 1 by sigma naught square minus 1 by sigma 1 square sigma xi square greater than some k1. Okay. I have adjusted some coefficient, so I am putting k1. Now if I am taking case 1, that is sigma 1 square greater than sigma naught square, then 1 by sigma naught square will be less than 1 by sigma 1 square. 1 by sigma naught square will be greater than 1 by sigma 1 square. So this will be positive. So in this case, the rejection region is sigma xi square greater than some k2, such that probability of sigma xi square greater than k2 under h naught, that is equal to alpha. So under h naught, so what is the distribution in the case of normal distribution? Sigma xi square by sigma square, that follows chi square n. So under h naught, this will become, so actually we can adjust here, this we can write this and this we can write as here. So this is chi square n. So if I am looking at the graph of a chi square distribution on n degrees of freedom, then this probability is alpha if this point is chi square n alpha. So the test function becomes, so the most powerful test is reject h naught if sigma xi square by sigma naught square is greater than chi square n alpha. So chi square n alpha point is the point on the chi square distributions curve, such that the probability beyond that is equal to alpha. Is that okay?
Yes, sir.
You can consider the other case also. In case 2, see, in case 2, what will happen? Sigma 1 square is less than sigma naught square. So 1 by sigma naught square will become less than 1 by sigma 1 square. So this will become negative. So the region will get reversed. So we can consider that part here. In case 2, the rejection region is of the form sigma xi square less than some k3, okay, where probability of this, that is sigma xi square less than k3, is equal to alpha. So if I am looking at the left hand side, then this point, that is chi square n 1 minus alpha, that is the probability on this side is alpha. So if I put this as divided by sigma naught square, then the test is reject H naught if sigma xi square by sigma naught square is less than chi square n 1 minus f. This is the most powerful test for this problem. Okay, so is this example clear to all of you?
Sir, I have a doubt.
Yes,
Sir,
yes.
in the function phi of x, when it is 0, sir, what does it mean? We are getting another condition of rejecting h naught.
Where it is 0?
Like the function phi of x is 0 when f of 1x is less than kf of f naught x. The most,
Phi of x is
then the definition of most powerful test.
yes, yes, yeah. What is the question? Yeah, this is the thing. Yeah, tell me what is the question?
Sir, when phi x is 0, aren't we accepting h naught?
Yes, we are accepting H naught. Yes, yes, we are accepting H naught.
Yes, sir. Okay, sir.
Yeah, I'm not writing everywhere. I mean, so I am writing rejected. So if that is not true, then it is accepted. Yes.
Yes.
I'm not writing here. These are continuous distributions. Actually, in the discrete distribution, at the point of equality, some condition has to be written. So that I am not writing right now because these are all continuous distributions. Okay.
Yes, sir.
Okay. So let me take maybe some alternative distribution. So let us take, say, let me take, say, exponential distribution. Let x1, x2, xn be a random sample from an exponential distribution that is equal to I e to the power minus x by sigma. Let me just explain also the previous one. Let me just give physical interpretation also. See, in this particular problem, in the normal 0 sigma square problem, if you remember, the maximum likelihood estimator for sigma square was 1 by n sigma xi square. It was also actually the UMVUE. And we have also seen that if I consider the best scale equivariant estimator, then it was 1 by n plus 1 sigma xi square. Okay. So sigma xi square is the quantity because it is also sufficient statistics, it is complete and so on. So that means the inference, or you can say the decision to for sigma square, it should be based on sigma summation xi square. And a smaller value of sigma xi square by n or larger value of sigma xi square by n, it will correspond to the smaller or larger values of sigma square. But how much exactly is the smaller and how much exactly is the larger, that is decided by the statistical formulation, and that gives you the cutoff points. So for example, when sigma 1 square is greater than sigma naught square, so actually what is happening is that we should reject for the larger value of sigma xi square. So now you see that how much large, that is determined by this point on the chi-square curve. Okay. So statistical formulation helps you to determine the exact cutoff points. Otherwise, see, your cutoff may be different than my cutoff. Okay. Like if I am testing sigma square is equal to 1 against sigma square is equal to 2, then somebody may say that, okay, if sigma 1 by n sigma xi square is less than 1.5, then I will accept h naught, and if it is greater than 1.5, then I will accept h1. Okay. But then somebody else may say, no, 1.5 is not good one. Let us do that because error should is, I don't want to be too big error, so I will make it 1.4. And somebody may say, okay, no, 1.6, let us make it. So that part is actually answered when we give this statistical formulation here. And then we are saying it is the most powerful test. That means for fixed size alpha, like if I say alpha is equal to 0.05, that means maximum error that I can allow for type 1 error is 0.05, then this is the most powerful test for this thing. See, this concept of type 1 error and type 2 error, you also try to understand from some real world examples. See, if I am considering, say, designing of a rocket chamber's strength, okay, so rocket chamber, because it will be used when there is a the send off is there, then there is a huge force that is implemented on that. So the pressure is created, and through that pressure, the chamber should be able to sustain that pressure, and then only it will be ejected to the space. If that is not happening, that means the chamber bursts. If the chamber bursts, then your mission fails. So now, what is the amount of error that can be tolerated, and what is the error that should be controlled? So the error can be on this side, that is the chamber size or the strength of the chamber, how much more it should be compared to the standard one, that means the strength thing. So if you say, okay, I can allow 0.05 error, then it is, that means out of every 100 missions, 5 missions are likely to fail. Okay, so how much error you can do? So okay, you may say it's fine, out of 100, 5 missions may fail, 95 will still work. But you compare it with the, say, trial of a medicine which is to be implemented for a patient. So for example, this actually disasters happened during this COVID disease, which everybody noticed. So initially it was told that if you take, say, some sort of plasma therapy, then people will be cured, and there was a huge demand for plasma. You might have noted in the a lot of people were contacting through Facebook and WhatsApp that this is required, and the plasma was sold, and then in the hospitals it was like infused to the patient, and huge costs were recovered, like 5 lakh rupees, 10 lakh rupees, and that kind of thing. So it became a big business. Now the outcome of the detailed study from Oxford University has come. It says that it did not reduce mortality at all. Okay. So that means it was completely, so the kind of error that has happened here, that has been allowed to creep in this one, is huge. Okay. So the question of this type 1 error, type 2 error is important because of this, because in a medical situation, this is very crucial. Similarly, if you consider the giving of some medicine called Remdesivir or something like that, and again there was a huge stockpile and a lot of black marketing was there, and the medicine was sold for single strips were sold for a few lakh rupees actually. But now the detailed study has shown that it has created a difference of only 0.02 mortality. So that means the persons who became actually serious and they were given Remdesivir, and those who were not given Remdesivir, the percentage difference between them is 0.02. So that means it is almost zero. Okay. So that is why the role of this type 1 error and type 2 error is quite important, and the statisticians are always worried about how much they should give the leverage, okay, for the type 1 error, and also the power of the test has to be calculated. That means the power of the most powerful test, it should be good. That means that type 2 error will be very small. So if the type 2 error is also very large, then there is no point. Although you may say it is the most powerful test, but if you don't calculate the power of the test, then it has no meaning. Okay. I hope I have made these points very clear. Let us look at this another practical problem. This is actually in exponential distribution. This is the mean life, isn't it? Sigma is the mean life. Expectation of x is equal to sigma here. So this is the mean life. Now we will like to test certain problem, like say sigma is equal to sigma naught. Let me write a general thing. Okay, against sigma is equal to sigma 1. Okay, and let me take again two cases. That means you may have case 1, sigma 1 may be greater than sigma naught, and case 2 could be sigma 1 is less than sigma naught. Okay. So in order to apply this Neyman-Pearson theory, let us write down the joint PDF of x1, x2, xn. So that is 1 by sigma to the power n e to the power minus sigma xi by sigma. Okay. So this ratio of the density functions at f1 and f0, that is 1 by sigma 1 to the power n e to the power minus sigma xi by sigma 1 divided by 1 by sigma naught to the power n e to the power minus sigma xi by sigma naught. And actually rejection region is, this is greater than k. Okay, so these are all known things, so we can adjust all these coefficients, take log also. So this will reduce to sigma xi 1 by sigma naught minus 1 by sigma 1 greater than some c. And again, if I am considering case 1, that is sigma 1 is greater than sigma naught, then 1 by sigma naught is greater than 1 by sigma n 1. So this region becomes sigma xi greater than, say, some c star, such that probability of sigma xi greater than c star under h naught is equal to alpha. Again, we will make use of our distribution theory here, because this distribution theory we worked out nicely in probability theory course, where we have actually found out the distributions of the sums of variables and so on. All those things we have done properly. So if we consider, see, if xi's are independent exponential distribution, what is the distribution of sigma xi? Do you remember that? What is the distribution of sigma xi? Gamma distribution. So if you look at sigma xi, that is following gamma n, and this lambda I we can write as 1 by sigma. Okay. So if we adjust this coefficient here, I put here sigma, then this will become 1 here. Okay. So this I can remove. This is simply 1 I will write. And then if I put 2 here, 2 times this, then this will become simply chi square 2n. See, what is gamma on n? That is 1 by gamma n e to the power minus y to the power n minus 1. So if I put 2y, then this will become y by 2 here, and then 2 here it will come 2 to the power n will come here. So this we can put as 2n by 2, this will come 2n by 2, this I can put as 2n by 2 minus 1. This is chi square kind of thing. So actually this is chi square 2n. So if we make this transformation, this gives us an easy way of interpreting, because I should use something for which standard tables etc. are available. Okay. So this becomes, so chi square 2n alpha point, that is this probability is alpha. So the most powerful test is to, reject h naught if 2 sigma xi by sigma naught is greater than chi square 2n alpha, which we can also write as 2n x bar by sigma naught greater than chi square 2n alpha. Is it okay? If you look at the physical interpretation here, see, in the exponential distribution, you know, of this structure that we have considered here, sigma xi is actually complete sufficient statistics. The MLE for sigma was x bar. So that means the decision for smaller or larger values of sigma will be based on smaller or larger values of x bar. And but exactly what should be the cutoff, for that this statistical theory helps to determine using the chi-square distribution. Similarly, in the second case, it will become less. So in the second case, the rejection region will be, if this is less than chi-square 2n 1 minus alpha, that is the left point. I hope I have explained these things properly. Are you able to understand this?
Yes.
Now, actually, you see this, that this simple type of statement, that is mu is equal to some value against mu is not equal to some value, or mu is equal to some another value. These statements we can actually determine the most powerful test here. But the problems can be little bit more general than this. Okay, that means the problems could be of this nature. Like in the normal distribution, I may say whether mu is less than or equal to certain quantity, or mu is greater than certain quantity. Or you may also say in place of mu is equal to, that means whether mu is equal to mu naught or mu is greater than mu naught. Or you may also say whether mu is less than mu naught, etc. Okay. This is actually called composite hypothesis, where you are not fixing any specific value. See, when you say mu is equal to mu naught, then it is a specified value. That is called a simple hypothesis. So the first result of Neyman and Pearson, that was about the simple hypothesis versus simple hypothesis case. But when the hypothesis is composite, then they try to extend the argument based on the nature of the distribution. For example, I mentioned in normal distribution, when we are doing the testing for the mean, then we said that x bar's large value leads to larger value of mu, the small value corresponds to small value of mu. So to formalize this, suppose I am writing down this kind of hypothesis here. That means whether my mean is less than some specified value or it is greater than another specified value. Again, if you look at in a sincere way, it looks that the null hypothesis corresponds to a smaller value of the mean, and the alternative hypothesis corresponds to larger value of the mean. So therefore, my test procedure which I developed should not change actually. The test procedure that I wrote here for this particular problem, that is, we reject for x bar greater than something. Okay, that should not change, because again x bar remains good estimator of mu, and the smaller values must correspond to the smaller values, the larger values should correspond to the larger value. Cutoff point is determined by the probability of the type 1 error being equal to alpha. So if we can ensure that even in the composite case, if the probability of type 1 error, here the probability of type 1 error is not one value, because mu can change, because we were calculating the distribution under h naught. Okay, so we will require the maximum such value. Now if the form of the distribution is of a particular nature, then one can ensure that the maximum value remains the same. That means at the same point. That is called families with the monotone likelihood ratio. Okay, so let me give you this definition. Fortunately, the standard distributions in statistics like normal distribution, Poisson distribution, binomial distribution, gamma distribution, exponential distribution, etc., they actually satisfy this property. This helped Neyman and Pearson to generalize their result, and whatever most powerful test they got for such one-sided hypothesis testing problems, they showed that the same test remains powerful at all the points, which we can call as the uniformly most powerful. Okay, so let me give a formal definition of the families with the monotone likelihood ratio. Maybe we can have a break for 5 minutes and then I will continue. So you can see the screen. No? You can see the screen.
Yes, sir.
Yes, sir.
So we consider the families of distribution with monotone likelihood ratio. So let us consider, see this family, family of the distribution, say fx theta, where theta belongs to some theta. Okay, this family has monotone likelihood ratio in, we will write like this, theta tx if fx theta 1 by fx theta naught is, if for theta 1 greater than theta naught, fx theta 1 by fx theta naught, this is an increasing function of tx. Okay, so then we say that the family is having monotone likelihood ratio. So let me give examples of the families. In fact, all the standard families that we are considering, they are actually having monotone likelihood ratio. So let me start with the, say, so suppose I am considering, say, family of normal distributions. Okay, normal mu1. So if I write down fx mu1 by fx mu naught, that is 1 by root 2 pi e to the power minus 1 by 2 x minus mu1 square divided by 1 by root 2 pi e to the power minus 1 by 2 x minus mu naught square. Here I am taking mu1 to be greater than mu naught. So this, of course, 1 by root 2 pi cancels out. You are left with e to the power and half. So x bar x square minus 2 mu naught x plus mu naught square, and then you have minus x square minus 2 mu1 x plus mu1 square. So this you can write, it is e to the power mu naught square minus mu1 square by 2, then e to the power mu1 minus mu naught into x. Since mu1 is greater than mu naught, this part is positive and this is of course constant. So this is increasing function in x. Okay. So therefore this family has, so the family has monotone likelihood ratio in theta x. So as a consequence, suppose I am considering x1, x2, xn. Okay. If x1, x2, xn is considered, like in the testing problem that I wrote for mu is equal to mu naught against mu is equal to mu1, then you have to write down the joint distribution. So x bar is having normal mu 1 by n, and then this will have maximum likelihood ratio in theta and x bar. Sorry, not theta, here it is mu. In mu x bar. Similarly, if I consider, say, the other example, that is normal 0 sigma square, and if I take say sigma 1 square greater than sigma naught square, and I write down the ratio, then it is 1 by root 2 pi sigma 1 e to the power minus x square by 2 sigma 1 square, 1 by root 2 pi sigma naught e to the power minus x square by 2 sigma naught square. So this is sigma naught by sigma 1 e to the power 1 by 2, well, x square into this 1 by sigma naught square minus 1 by sigma 1 square. So if I am taking sigma 1 square to be greater than sigma naught square, then 1 by sigma naught square is greater than 1 by sigma 1 square. So this is increasing in x square. Okay. So this has monotone likelihood ratio in sigma square x square. So if I am considering the sample x1, x2, xn following normal 0 sigma square, then what the statement will be? It has MLR in sigma square, sigma xi square. Okay. Are these exercises clear?
Yes, sir.
And based on this, actually, the generalization of the Neyman-Pearson result was done, and that says that if the family of distribution has monotone likelihood ratio, then for the composite versus composite, where the hypotheses are one-sided, then you have uniformly most powerful test procedures. So let me state the theorem. Suppose we have the PMF or PDF, say fx theta with MLR in theta tx. Okay. Then for testing H naught, theta less than or equal to theta naught versus theta greater than theta naught, the uniformly most powerful test that is UMP is given by phi x is equal to 1 if Tx is greater than C, it is gamma if Tx is equal to C, and 0 if Tx is less than C, where C and gamma are determined by that probability of basically Tx greater than C plus gamma times probability Tx is equal to C is equal to alpha. Let me show you the applications here.
So the probability will be with respect to H naught, right?
Under H naught, right? It is under H naught. So basically supremum of this, basically, because under H naught you are having several points here. Okay. But what happens that the maximum value is attained when theta is equal to theta naught. So this supremum, that is why I did not write here. Actually, I had to write supremum of this is equal to alpha. But the supremum is attained when theta is equal to theta naught because of the monotone likelihood ratio. Anyway, I am not giving the proofs of these theorems because they involve a lot of measure theory. I mean, a lot of measure theory and a lot of concepts are there. at your level, you still don't have that much mathematical background. So that is why I am not carrying out these calculations here. But now you see, if I am considering, say, normal distribution problem itself. So let us go back to this problem here. X1, X2, Xn follow normal mu1, this particular problem. If I consider this problem, then even for this problem, because the family of distribution has monotone likelihood ratio in mu and x bar, and therefore if I consider the hypothesis mu less than or equal to mu naught against mu greater than mu naught, then the test function will be same. So that is, if I consider x1, x2, xn follow normal mu1, and I am considering the hypothesis testing problem mu less than or equal to mu naught against mu is greater than mu1, then the test procedure is UMP test of size alpha is to reject H naught if root n x bar minus mu naught is greater than Z alpha. Okay. Similarly, you can write for the variance part also. If I am looking at this problem x1, x2, xn following normal 0 sigma square, then for testing sigma square less than or equal to sigma naught square against sigma square greater than sigma naught square, then the UMP test of size alpha is reject H naught if sigma xi square by sigma naught square is greater than chi square n alpha. Okay, I think this is fine. So if we consider, say, exponential families of distributions, okay, if we consider exponential families of distributions, that is fx theta is equal to say some c theta hx e to the power theta tx. Okay, if we are considering this type of distribution, then this has monotone likelihood ratio in theta tx. Okay, so for monotone likelihood ratio, since this previous result is true, therefore whenever the family of distribution belongs to the exponential family of distributions, for one-sided testing of hypothesis problems, we can always find out the uniformly most powerful test procedures. We can have a little bit more complicated situation also. Okay, a little bit more complicated in the sense that we can have two-sided hypothesis. That means either the null hypothesis or the alternative hypothesis, they can be two-sided. If they are two-sided, then things become slightly more complicated. So let me just talk about this in a brief. Although the full theory is slightly complicated, it is involving certain additional concepts which at your level you have not done, and it will be difficult for me to explain full proofs of or even the full statements of those things. However, let me briefly mention about that part, because at least you should know the statements of such things. When we have two-sided alternative, like if I consider theta is equal to theta naught against theta 1 is not equal to theta naught. So alternative is actually two-sided, because rejection happens either if theta is less than theta naught or if theta is greater than theta naught. Then the UMP test does not exist. Okay. If it doesn't exist, then what happens? So in that case, we try to restrict the class of test functions. Like in the case of estimation, you have seen that we restrict the attention to class of unbiased estimators and try to find out the best choice. Similarly, we can try to find out using invariant estimators, find out the best choice. Or we have other principles such as Bayesian principle and the minimax-t principle. All those concepts are valid even for the case of testing of hypothesis. So we define a test to be unbiased test if probability of rejecting H naught when under H naught, this is always less than or equal to alpha. So now, because this can be several points, no, H naught is composite in general, and if probability of rejecting H naught under H1, this is always greater than or equal to alpha. That means this is the size is always less than or equal to alpha, and the power is always greater than or equal to alpha. Such a test is said to be unbiased. So in the two-sided hypothesis testing problems, generally we impose such conditions. And if we impose such conditions, we actually get the most powerful test within this class. They are called uniformly most powerful unbiased tests of hypothesis. So UMP unbiased tests exist for two-sided hypothesis testing problems. In exponential families. Now in the remaining part of this lecture, actually, or even in the next lecture, I need to write down the standard test functions for the problems of parameters in the normal distributions, say binomial distribution, exponential distribution, etc. So remaining part I will try to write all the cases so that at least you can implement them in. So tests for so firstly we consider one population model. Let x1, x2, xn follow normal mu sigma square. Okay. So case 1, we take sigma square is known. If sigma square is known, then we have actually earlier given the solution when I put the value of sigma square is equal to 1. But in general, some value can be there, like it can be 3 or it can be 10 and so on. So let me write down the procedure for a general case. So I define z is equal to root n x bar minus mu by sigma. Okay. This actually follows normal mu, normal 0, 1. Okay, this follows normal 0, 1. So let me consider some testing problems. So I'll write testing problem 1. H naught is mu is less than or equal to mu naught against mu is greater than mu naught. For this, the test is reject H naught if Z is greater than Z alpha. So Z is already defined here, root n x bar minus mu by sigma following normal 0, 1. Then let us consider testing problem 2, where mu is less than or equal to mu naught is replaced by mu is greater than or equal to mu naught. So I am interchanging the role. Some student was asking the question that which should be my null and what should be alternative. So there is nothing hard and fast about that. We can actually have the reverse situation. So here the rejection region will be Z is less than minus Z alpha. Here some students may ask that whether I should have Z greater than or equal to Z alpha or Z greater than, strictly greater than. The answer is that both of them are okay, because in the case of continuous distribution, the equality at a point does not make any difference because the probability of that point is 0. So in real life situation, when the data is given, it is not possible that Z is equal to Z alpha. Okay, so because Z alpha you are seeing from the tables, but if you increase the accuracy, whatever Z value is coming, it will not be equal to that. So let me write the other testing problem, that is two-sided, that is mu is equal to mu naught against mu is not equal to mu naught. For this one, the rejection region is two-sided. So reject H naught if mod Z is greater than Z alpha by 2. That means we are on this side or this side. Okay, that is alpha by 2 here. Then you reject, within this it is acceptance region. These are the uniformly most powerful unbiased tests for these problems. Okay. Now let me move to case 2. In case 2, I am taking, see case 1 what I wrote here, sigma square is known. So in the case 2, sigma square is unknown. Okay. So let us put it here, sigma square is unknown. Here I have to change the statistic here. It is root n x bar minus mu naught divided by. So just let me see here what I wrote here. See, this one I need to modify here, because if I am writing Z is less than Z, greater than Z alpha, then the value should be calculated. So here I did not write mu naught. So I should write here mu naught, because the distribution has to be calculated under H naught only. Okay. So it is x bar minus mu naught by sigma. So similarly here also it will be this, but here it will come S. So under H naught this will follow T distribution on n minus 1 degrees of freedom. So for the testing problem 1, reject H naught if T is greater than T n minus 1 alpha, because T distribution is also a symmetric distribution. So you will get this kind of points. For testing problem 2, it is reject H naught if T is less than minus T n minus 1 alpha. And for the testing problem 3, it is reject H naught if mod of T is greater than T n minus 1 alpha by 2. these tests are uniformly most powerful unbiased tests. I am not giving the full derivations here because I need to build up a lot of theory here, but I don't have sufficient mathematics at this moment for you, which I can give at this point. So I am just skipping that, but we can solve problems based on these procedures. Similarly, let us consider the testing problems for variance here. So I am taking case 3 where mu is known and my testing problems is, let me write TP4 H naught sigma square is less than or equal to sigma naught square against H1 sigma square is greater than sigma naught square. The test procedure is based on, let me write here this statistic as say some u is equal to sigma xi square by sigma naught square. This actually follows chi square n under H naught. So the test procedure is based on that, and we will say reject H naught if u is greater than chi square n alpha. For the testing problem which is complementary of this, that is sigma square less than or equal to greater than or equal to sigma naught square against H1 sigma square is less than sigma naught square, we reject H naught if u is less than chi square n 1 minus alpha. And for the two-sided problem, the test procedure becomes two-sided, that is reject H naught if u is less than chi square n 1 minus alpha by 2 or u is greater than chi square n alpha by 2. Since chi square distribution is not symmetric, so I have to take this alpha by 2 and 1 minus alpha by 2 points. In a normal and t distribution, it was simply minus value, but here it is not. In this case also, when sigma square testing is being done, but mu is unknown, then these procedures will change here. Actually, I have taken mu to be 0 here. If mu is not 0, then I have to substitute here, and you can actually write down the statistic as xi minus mu square by sigma naught square. But I don't want to create that complication here, so I have just put mu is equal to 0. And in the fourth case, when mu is also unknown, then we will consider this n s square, that is equal to 1 by n minus 1 sigma xi minus x bar square. So basically this w is n minus 1 s square by sigma naught square. That follows chi square distribution on n minus 1 degrees of freedom under sigma square is equal to sigma naught square. So the most powerful test for the 4 problems, that is for the fourth problem, you will have rejection region based on w, that is reject H naught if w is greater than chi square n minus 1 alpha, and for fifth problem it is the reversed, so reject H naught if w is less than chi square n minus 1 1 minus alpha, and for the two-sided problem it is reject H naught if w is less than chi square n minus 1 1 minus alpha by 2 or w is greater than chi square n minus 1 alpha. I have given you the standard tests for the 1 parameter problem or 2 parameter problem in the normal distribution, but this is related to single population. Now more general problems occur if I have 2 population or even k population models. So in that case, I may have to compare the means of 2 normal populations or the variances of 2 normal populations or the means and variances of k normal populations, etc. So in the next class, I will give you the test procedures for these things and also certain non-conventional distributions also. So I think we are actually missing some classes because again tomorrow there is a holiday, I think. Is it holiday declared tomorrow?
Yes, sir.
Yes, sir.
Yeah, last week also abruptly there was a holiday, so I missed the class. So I had asked you people to give me some additional time, but you have not given me. Can we have some class on some other alternative day, maybe late evening or something like that? Monday, Tuesday?
Sir, you can record a lecture and provide us. We can watch it.
Okay, okay, then I will do that. Okay, fine. Yeah,
Yes,
because
sir.
because a lot of things are left out, so I need to cover it quickly. Okay, fine. Let me stop the class here.